Hello, welcome to this new lecture of the course Transportation Network Analysis. So, in the last class we had started to discuss about some important concepts related to continuous optimization because that will be useful later for solving traffic assignment problems. So, we were discussing about this concept of convex functions. So, let us continue there. This is an example of a function which is not convex. So, this function zx equal to minus x square is not convex. So, this is the plot of this function here. So, we can pick any two arbitrary points, suppose a and b, and you will be seeing that any point that you pick here, suppose on this line segment, suppose this point c here. So, the corresponding point on this function, suppose d here. So, this is lying above c. So, therefore, it is not a convex function. Okay. But this zx equal to minus x square is a concave function. Okay. So, I had also mentioned that there is something called concave function also. Okay. Okay. Now, a function is said to be strictly convex if the line segment between any two points of the function lies above the function between the 2 points. So, try to see this definition more precisely. So, you will see that there is not that much difference between a convex function and a strictly convex function. The only difference is that here the line segment between any 2 points of the function will lie above the function between the 2 points. Okay. Whereas previously we were saying that this line segment between any 2 points of the function will not lie below the function between the 2 points. So, now in the case of strictly convex function, we do not want this line segment touches the corresponding point on the function at any point between those corresponding points, arbitrary points a and b. Okay. So, for example, this function zx equal to x square that we had seen like this. So, this is a convex function also, but this is strictly convex function also, because if you pick any two arbitrary points here a and b and you choose any point between a and b, suppose this point c, this is above the corresponding point on this function d. Okay. But an example of a function which is convex but not strictly convex is like this. This function of zx equal to 2x plus 3 that we had seen here. So, if you pick any 2 points arbitrary on this function here, then if you connect the line segment between those 2 points a and b, then any point on this line segment will lie exactly on the corresponding point of that function, which we do not want in the case of strictly convex function. We want that this line segment should always be above the corresponding points on the function. Okay. So, therefore, strictly convex condition is more tighter than or more restricted than the convex function case, and therefore, a strictly convex function is always a convex function, but vice versa may not be true. Okay. So, here you can see that this function zx equal to 2x plus 3, this is a convex function, but it is not strictly convex. Okay. But if I tell you that a function is strictly convex, it is automatically a convex function also. Okay. Mathematically, to say that a function z is strictly convex means this thing, that z of theta x1 plus 1 minus theta x2 is less than theta zx1 plus 1 minus theta zx2 for any arbitrary x1 and x2 and for any theta which lies in the interval 0 to 1. Okay. So, the change that has happened from the case of convex functions is that now we have this less than sign here. Previously, we had less than or equal to in the case of convex functions. Okay. So, this is saying the same thing. Now, we have a strict inequality between the two terms here. So, the functions x square and e to the power x are strictly convex, but this function 2x plus 3 is not strictly convex. Okay. Now, if a function z is twice differentiable, then it is convex if and only if the second derivative of this function z with respect to x is greater than or equal to 0 for all x, and it is strictly convex if and only if the second derivative of z with respect to x square is positive for all x. Okay. So, now suppose if we have to argue that a function is convex, suppose. Okay. So, if you have to do that, then if we go back to the first definition of convexity that we had seen, that you pick any two arbitrary point on this function and the line segment connecting those 2 points should never lie below the corresponding point on the function. Now checking that condition may not be easy for every type of function, because verify that this condition holds for any arbitrary points x1 and x2. Okay, so where any arbitrary points we need to draw a line segment, and then we need to see that whether on all of the points on this line segment we are having the line segment to be above than the corresponding point on the function. So just checking this is not possible because there can be infinite arbitrary pair of points. Okay, so then we have to prove that condition, okay, mathematically, but even proving that may not be that easy in many cases. So therefore this kind of definition is useful. So if we know that a function is twice differentiable, then it is convex if and only if the second derivative of this function z with respect to x is greater than or equal to 0 for all x. Okay, and for strict convexity this reduces to this second derivative being positive. Okay, so now this simplifies the life a lot. So now we just have to compute the second derivative, and if we see that it is greater than or equal to 0 for all the x values, then this function is convex given that it is twice differentiable. Okay, note that if we have to argue that a function is not convex, then that is easier, because then we just need to come up with any one set of arbitrary points, and we need to come up with just one point on the line segment connecting those two arbitrary points where the value on this line segment is going below the corresponding point on the function. Okay, so if you think that function is not convex, then it is easier to check, whereas if you think that it is convex, then we need to prove it either through the original definition that we have, or if the given function is twice differentiable, then we can check this kind of condition here. Okay, that the second derivative whether it is greater than or equal to 0 or not for all x. So previously we had seen 3 examples of convex functions x square, e to the power x and 2x plus 3. Fortunately all of these functions are twice differentiable. So let us determine the second derivatives of these functions. So the second derivatives of these 3 functions are 2, e to the power x and 0, and all of these values are always greater than or equal to 0 for all x. So therefore it is confirming to our belief that all of these functions are convex. Okay, but these 2 functions x square and e to the power x are strictly convex, but 2x plus 3 is not. Okay, because the second derivative of 2x plus 3 is 0, and that is not positive for all x. Okay. Okay. Now a sufficient condition for a stationary point x star to be a local minimum is that the function zx be strictly convex in the vicinity of the stationary point. Okay, so important thing to note that this is a sufficient condition. So if we think that a stationary point x star is strictly convex in the vicinity of a stationary point x star, then that point is local minimum. However, if this is not satisfied, this does not mean that the function will not be a local minimum at x star. Okay, so this is a sufficient condition. So this is trying to ensure more than enough to have that a stationary point x star is a local minimum. Okay, so if function zx is twice differentiable around the stationary point x star, then the sufficient condition is that second derivative of z with respect to x is positive at x equal to x star. Okay, so this kind of simplifies our life, because if we are able to argue that at x equal to x star the second derivative is positive, then we can be sure that this stationary point is in fact a local minimum. Okay, because this is kind of a condition which is required to ensure that this point x star will also be a global minimum. It has to be a local minimum first, and then if it works out, it might also turn out to be the global minimum. Okay, so you can see that this condition is satisfied at points a and d here. So what does second derivative being greater than 0 at x equal to x star means? So that means that the rate of change of slope is positive. So the rate of change of slope is in fact positive at both of these points a and d. So the slope here on this side of a is negative, okay, for this function, whereas it is positive here, and so the slope is negative and it is slowly turning to 0 here, and then it is becoming more and more positive here, and therefore the second derivative of this function at this value, this point a, is positive, and the same holds at this point d also. Okay, and therefore they are local minima, both a and d. Now if there are multiple local minimum, then usually it is difficult to demonstrate that a particular local minimum is also global. Okay, because that will require identification of all the local minima. So then we need to be sure that what all local minimum are present, and then we need to compare among them in order to argue that one of them is in fact the global minimum. However, if we are lucky that there is in fact just a single local minimum for that function, then we are also sure that that will also be the global minimum. Okay. So therefore, to demonstrate that a local minimum is unique, it is sufficient to show that Zx is convex for all x. Again, this is another sufficient condition. So if we are lucky that we just have a single local minimum, then we will be sure that will also be the global minimum. Okay. So in order to ensure that a local minimum is unique, a sufficient condition is that Zx is convex for all x. Now that does not mean that if this condition is not satisfied, then a local minimum cannot be unique. Okay. So this is again a sufficient condition. This is trying to enforce more than that is required. Okay. This is not a necessity and sufficient condition. Okay. Now notice the difference here. It is saying that to argue that a local minimum is unique, it is sufficient to show that the Zx is convex for all x. Whereas if we had to argue that a stationary point x star is local minimum, we just had to argue that at x equal to x star, the function is strictly convex. Okay. So there we had to argue strictly convexity at that point x star or around that only. Okay. Whereas here we have to argue that this function Zx is convex for all x in that whole domain that x can take. Okay. So there is a that difference here. Okay, so until now we were talking about unconstrained optimization, that is we do not have constraints, but when there was single variable. So this function z was only varying with x, and therefore we could plot these two dimensional diagrams where we were having zx on the y axis and x on the x axis. Okay, so now we will be considering these multivariate functions here, that is the objective function is given by zx where x, this bold vector, is consisting from x1 till xi. Okay. Now the conditions to establish minimum are analogous for multivariate functions as that of single dimensional functions. So now you will be thinking that why did we just directly start with these multivariate functions if everything is going in the same way? The reason behind that is when there is single variable, then it is easier to understand concepts. For example, when we had introduced in first order condition, that is a necessary condition for a point to be a minimum. So then we had said the derivative of the function is 0. That is, slope of that function is 0 at x equal to x star. So that kind of definitions many people might have already seen before, okay, for unconstrained optimization case. But for the case of multivariate functions, that is when the function is varying with many variables, then it becomes slightly more involved. Okay. So the necessary condition for a function zx to be minimum at x equal to x star is that the gradient of this function should be equal to 0. Now this is a 0 vector. What does this mean? That each of the partial derivative of this function z with respect to these individual variables should be equal to 0. Okay. So if a function z is varying with x1 and x2, what does this gradient of z at x star equal to 0 means? It means that the partial derivative of this function z with respect to x1, this should also be equal to 0 at x1 star, x2 star, and the partial derivative of z with respect to x2 should also be 0 both at x star, I mean this is a bold, equal to x1 star comma x2 star. Okay. So there are these two 0 here, and that is why this is 0 vector here. This is consisting of two zeros here if we have two variables. So this necessary condition is the same as the first order condition, so which ensures that at point x equal to x star we have a stationary point. Okay. Now since this is a necessary condition, this does not mean that it has to be a local minimum, okay, because we have seen before that every stationary point need not be a local minimum. Let us consider this example here, this function which is varying with x1, x2. Now the gradient of this function at every point x1, x2 is given by this. So how did this come? We first took the partial derivative with respect to x1. So here we will get 2x1, then from here you will get 2x2 and then minus 2. Similarly, we will get 4x2 here, then 2x1 from here and then minus 4. Okay. So now each of these two terms have to be equal to 0. So we equate this to 0 and we equate this to 0. When you will solve both of these two equations, we will be getting that at x star equal to 0 comma 1, this is the stationary point of this function. Okay. Now the definitions of convex and strictly convex functions also remain analogous for the multivariate functions. So function is said to be convex if this z theta x dash plus 1 minus theta x double dash is less than or equal to theta x dash plus 1 minus theta times z x double dash for any x dash and x double dash and any theta that lies in 0 to 1. Okay. So again it is same in that way. The only difference here is that now these x dash and s double dash, these are vectors here. Previously these were single variables x1 and x2, but now these are vectors here. That is the only difference. Otherwise mathematically the condition is the same. Okay, so this is what it is saying, x dash and x double dash are vectors here. Now a function is strictly convex if z theta x dash plus 1 minus theta x double dash is less than theta times zx dash plus 1 minus theta times x double dash. Okay, for any x dash and x double dash and for any theta which lies in 0 to 1. Okay, again this is going in the same way that we have defined strictly convex function, just that now these x dash and x double dash are vectors now, unlike single variables that were before. Okay, to show that the stationary point x star is a local minimum, it is sufficient to demonstrate that zx is strictly convex in the vicinity of x equal to x star. Okay, same as it was the case in the single dimension case. Now, how to check that a function is strictly convex in the vicinity of x equal to x star? Now, if the function is twice differentiable, then zx is strictly convex around x equal to x star if the following matrix is positive definite at x equal to x star. Now, this is that matrix. So, here you can see that we have these second order partial derivatives. So, for example, this first term is first taking the partial derivative with respect to x1 and then again taking the partial derivative with respect to x1. The second term in this first column will be that you take the partial derivative z with respect to x1 and then take the partial derivative with respect to x2. Okay. Then the third term in this same first row will be you take the partial derivative of z with respect to x1 and then you take the partial derivative with respect to x3. Okay. Now, if you look at the leftmost term in this second row, then we will be having this partial derivative of z with respect to x1, x2 and then with respect to x1, okay, and so on. So, you will be seeing that these diagonal terms here will be these partial derivatives where both of these partial derivatives are with same type of variables, whereas at all the other places in this matrix we will be having these mixed partial derivatives. So, this matrix is called the Hessian matrix of Zx. Okay. Now, a matrix M is positive definite if x transpose Mx is positive for every non-zero vector x. Okay. Now, let us understand what is a symmetric matrix, although many of you might already know this. So, if a matrix is said to be symmetric if an element in the ith row and jth column is the same as the element in the jth row and ith column. Okay. So, this is an example of a symmetric matrix because here you can see that the term in the first row and second column is the same as the term in the second row and first column. Okay. So, now if you have to check that a matrix is positive definite, using this definition is not easy because you have to argue that x transpose Mx will be positive for every non-zero vector x. So, therefore, there are many equivalent definitions of positive definite matrices given that this matrix M is also symmetric here. So, a symmetric matrix M is positive definite if and only if all the eigenvalues of M are positive. Okay. Another equivalent definition is that all the upper left submatrices Mk have positive determinants. Okay. Now, these terminologies are related to linear algebra. If you do not remember these, I will suggest that you pick up any standard text on linear algebra and you will be able to understand these. One such text is by Gilbert Strang on linear algebra and its applications. Okay. So, you can read from this also. So, let us take an example here. Suppose you have a matrix, this one. Now, you can see that it is a 2 cross 2 matrix. It is a symmetric matrix because we have these two elements here. Now, let us determine whether this matrix is positive definite or not using the second equivalent definition that we have. Okay. So, let us determine the left submatrices here. The first left submatrix is this matrix which just consists of the element 4, okay. And then the second left submatrix is this matrix which consists of this whole matrix itself, okay. Now we need to determine the determinants of these two matrices. So the determinant of this matrix is 4, whereas the determinant of this matrix is 4 times 3 minus 2 into 2, which is 8, which is positive. So since the determinants of both these left submatrices is positive here, so therefore this matrix is positive definite, okay. Now finally, in order to show that the local minimum is unique, it is sufficient to demonstrate that the function is convex everywhere, okay. So it is the same thing that we had said when we were focusing on univariate functions also, that is where the functions just vary with single variable. So it is again a sufficient condition. So if we are able to argue that there is a single local minimum in a function, then automatically that will also be the global minimum, right. And in order to ensure that local minimum is unique, I mean there is in fact a single local minimum, a sufficient condition is that the function is convex everywhere, okay. Now how to argue that a function is convex everywhere in this multivariate function? So we have seen this Hessian matrix, right. Now what we need to argue, that this Hessian matrix is positive semi-definite. This is very close to the definition of a positive definite matrix. That's the only difference here is that, see, now a matrix M is said to be positive semi-definite if X transpose Mx is greater than or equal to 0 for all vector X. Okay. So you can see that now this equality is also coming here. Similarly, in the equivalent definitions that we had seen for the positive definite matrices, we can extend the same way for positive semi-definite also. So one equivalent definition is that a matrix M which is symmetric is said to be positive semi-definite if all of the eigenvalues are non-negative now. So previously for the positives definite we were saying they had to be positive, now we are saying greater than or equal to 0, non-negative. Similarly, these left submatrices, all of them should have non-negative determinants in order to have a positive semi-definite matrix, given that this matrix is also symmetric, okay. But note that this has to hold at every x here. So the Hessian matrix should be positive semi-definite at every x in order to argue that the function is convex everywhere, okay. So this is different from the case when we have to just argue that the function is strictly convex at x equal to x star, okay. So there we have to just argue that the matrix is positive definite at x star, but here we have to argue that the matrix is positive semi-definite at all x, that is the difference, okay. So with this we will be ending this lecture here. Thank you.